We live in a world of three dimensions, up and down, side to side, backward and forward, or any other three directions that are at right angles to each other. It's easy to imagine something in one dimension like a straight line, or two dimensions such as a square drawn on a sheet of paper, but how can we possibly learn to see in an extra dimension to those we're familiar with, a fourth dimension? Where is this additional direction that's perpendicular to the three we know? Sometimes the fourth dimension is taken to be something other than an extra direction in space. After all, the word dimension, from the Latin dimensionum, means simply a measurement. In physics, the basic dimensions that form the building blocks of other quantities are considered to be length, mass, time, and electric charge. Very often in a different context, physicists talk about three dimensions of space and one of time, especially since Albert Einstein showed that in the world in which we live, space and time are always bound up together in a single entity called space-time. Even before the theory of relativity came along, though, there had been speculation about the possibility of being able to move backward and forward along the dimension of time, just as we can move any way we like in space. In his novel, The Time Machine, published in 1895, H.G. Wells explains that an instantaneous cube, for instance, can't exist. A cube that we see moment by moment is just a cross-section of a four-dimensional thing having length, breadth, width, and duration. There is no difference, says the time traveller, between time and any of the three dimensions of space, except that our consciousness moves along it. Here, though, we're going to focus on dimensions in space. Our failure to be able to visualize higher dimensions makes it tempting to think that the fourth dimension is somehow mysterious. But mathematicians have no trouble in working with four-dimensional objects or spaces, because they don't have to imagine what they're actually like in order to describe their properties. These properties can be figured out quite easily using algebra and calculus. Start with a circle, for instance. A circle is a curve made of all the points in a plane that are at the same distance, the radius, from a given point, the centre. Like a straight line, it has only length, no width or height, and so is a one-dimensional thing. Imagine yourself positioned and constrained within a line. The only freedom of movement you'd have is along the line one way or the other. It's the same with a circle. Although a circle exists in a space of at least two dimensions, if you were positioned and confined within the circle, then you'd have no more or less freedom of movement than if you were positioned within a line. You could only go back and forth along the circle, effectively tied down to a single dimension of movement. Non-mathematicians sometimes think of a circle as including its interior as well. But a filled-in circle to a mathematician isn't a circle at all, but a very different object called a disk. A circle is a one-dimensional object that can be embedded in a two-dimensional object, a plane. A finely drawn circle on a sheet of paper is an approximation to this. The length or circumference of a circle is given by 2 pi r, where r is the radius, and the area enclosed by the circle is pi r squared. Moving up a dimension, we come to the sphere, which consists of all the points lying at the same distance in three-dimensional space from a given point. Again, the layperson may confuse an actual sphere, which is just a two-dimensional surface, with the object that also includes all the points inside this surface. But once more, mathematicians make a sharp distinction and call the latter a ball. A sphere is a two-dimensional object that can be embedded in three-dimensional space. It has a surface area of 4 pi r squared and encloses a volume of 4/3 pi r cubed. Because an ordinary sphere is two-dimensional, mathematicians call it a two-sphere, whereas a circle, using the same naming system, is a one-sphere. Spheres in higher dimensions are said to be hyperspheres, and can be labelled in the same way. The simplest hypersphere, the three-sphere, is a three-dimensional object embedded in four-dimensional space. We can't capture this in our mind's eye, but we can understand it by analogy. Just as a circle is a curved line, and an ordinary sphere or two-sphere is a curved surface, a three-sphere is a curved volume. Using some straightforward calculus, mathematicians can show that this curved volume is given by 2 pi squared r cubed. It's the three-sphere equivalent of the surface area of an ordinary sphere, and is also referred to as a cubic hyperarea or surface volume. The four-dimensional space enclosed by a three-sphere has a four-dimensional volume or quartic hypervolume of a half pi squared r to the fourth. Proving these facts about the three-sphere is no more difficult than proving them about the circle or ordinary sphere, and doesn't involve having to understand what a three-sphere actually looks like. Likewise, we have no way to grasp the true appearance of a four-dimensional cube or tesseract, but it's straightforward to describe the progression from square to cube to tesseract. A square has 4 vertices or corners and 4 edges. A cube has 8 vertices, 12 edges and 6 faces. A tesseract has 16 vertices, 32 edges, 24 faces and 8 cells, the three-dimensional equivalents of faces, consisting of cubes. This last fact is the one that defies our attempts at visualization. A tesseract has 8 cubic cells arranged in such a way as to enclose a four-dimensional space, just as a cube has 6 square faces arranged so as to enclose a three-dimensional space. This is the first of a 3-part series on the fourth dimension and is based on one of the chapters of my book Weird Maths. Thanks for watching, I'll see you again soon.